Okay, thank you very much. I am a K-Stater at KU, and I got to tell you, when I first went there, it's kind of like having a rock in your shoe. It didn't quite hurt, but I got used to it now. It's all good. Life's good. So this is about Kansas anyway, so that's what I'm up here for. So my part of the program really is to kind of set the stage of the aquifer conditions, what we see, and what it might look like in the future. You know, we talk about Ogallala, we talk about high plains, what's the difference with that. So I'm going to move through some of these pretty quickly. If you see something that you see, go ahead and write it down. I'm a fast talker, I move pretty quick. Write it down, come find me, some other people up here, or anybody with the state and other organizations. We'll get some questions answered for you. And I don't think this is the same clicker I got. There we go. I like to start off with this map showing what we call the normal precipitation. And normal precipitation is just the average over the last 3 full decadal period. And in Kansas, we have quite the gradient. Western Kansas, we're running about 15 to 16 inches of precipitation a year. By the time you move over into the eastern side of the state, you know, especially down in Cherokee County in the Ozark Plateau, you're talking 45 to 50 inches a year. And so this has a big influence on how water is used across the state. I'm clicking. There we go. This is the map, and it's showing you, on average, what the water is, how much water is diverted within each county, and then what it's used for, the proportion of it. You know, our big population centers in south central Kansas and in the Kansas River Valley with Kansas City area and Topeka, that's where we see a lot of municipal and industrial type applications. When you move down into western Kansas and the south central Kansas, you see the biggest user of water in Kansas is for irrigation purposes. And again, precipitation is driving this. If you flip our precipitation patterns, I guarantee you, you wouldn't see that level of development. So there's a need there for water for irrigation in western Kansas, but there's also, you have a need, you also have to have the means to do it. And that's what this map is showing. It's showing you the proportion. The size of the circle here doesn't matter. What matters is the ratio that's happening inside there. The more red you see indicates more of that water is coming from a surface water source, a river, a stream, some type of impoundment. If it's blue, it's coming from a groundwater source. And especially the ones in western Kansas and south central Kansas, you know, they overlay this gray looking thing underneath there. That's the saturated extent of the high plains aquifer. And it's the primary water source for almost all the uses that's overlying it. Now, the Kansas High Plains Aquifer, well, the High Plains Aquifer itself is enormous. It's one of the largest, most accessible freshwater aquifer systems in the entire world. It runs all the way from South Dakota down to Texas. And in Kansas, it has a sizable footprint. Now, a lot of times you'll see people describe the aquifer as a vast underground reservoir of water. And people actually have the perception that if they put on scuba gear, went down a well, they can swim around in this cavern of water. There's areas of states that's like that, but not here. In Kansas, a lot of this is material that's come down from the Rocky Mountains, clays and silts, sands and gravels, and it's filled with water. And that's your aquifer. In Kansas, we kind of make a distinction with the High Plains Aquifer. In the western part of the state, my clicker here, we generally refer to as the Ogallala portion of the High Plains Aquifer. And as you move into south central Kansas, you start to get into what we call the Great Bend Prairie Aquifer, and then later the Equus Beds Aquifer, which is the primary water source for the city of Wichita. Again, this is all hydrologically connected with water, but the Ogallala is a very different animal than south central Kansas is. And again, a lot of that is dealing with that precipitation patterns we saw. It's important to us that we have an extensive water level network at the state level. There's a lot of other sub-networks as well, but we work with the Kansas Department of Agriculture, their Division of Water Resources, and measure about 1,400 water wells each year. In addition, the governor mentioned the micro-level variations that we see in the aquifer also. We also have a program funded through the Kansas Water Office called the Index Well Program, where we have wells that are sitting, continuous recorder wells that are sitting out in the state. There's 3 of them. And they constantly track what the water level is doing, and it's given us great insight to what's happening to the water table underneath there. And we post these every 2 hours we have a measurement sent to us via satellite. GMD4, www.gmd4.org. They post their hydrographs that we see just south here, Colby, right there on the front of their website. So it's given us great insight at the local level. But by and large, what you can see today comes from this vast resource of 1,400 wells that we measure every year. Now, if you take the depth of water measurements, on average across the High Plains Aquifer, it's about 100 feet deep. But averages are made up of extremes. So you move in the eastern part of the Equus Beds, you're talking less than 50 feet, less than 20 feet. as you move in the Ogallala is very variable depending on where you're located at. The deepest parts are down south of Haskell County, where we just started across about 400 feet down to water. When you take into account the land surface elevation, you get the elevation of the water table. And water underground behaves the same as below the ground. More times than not, it's going to go downhill. So most of our gradients are from west to east. And since pre-development time, since the 40s and the 50s, we've seen some significant drops in that water table, 100, 150 feet, getting to 200 feet. And a lot of that, again, deals with the lower precipitation patterns and also the lower recharge rates. You don't see that so much in south central Kansas, but you do see it in the Ogallala portion. And again, a lot of it goes to the recharge rates. A lot of people like to talk about recharge, and it's something really hard to quantify, but generally we say in the Ogallala portion of the high plains, we're talking about ½ an inch a year. And that's on a good year. That's not really a whole lot of water that we're talking about. So we're in a deficit environment for the Ogallala. And so this map then it kind of shows you some of the more current trends of what's going on. We call this the wiggly map. And it's just accumulating that water level change over time. And if in areas in blue, you see it's an increase in the water table. Areas that are green, the yellows, the reds are indicating a decline in the water table. And so here you can see the difference between the Equus Beds, Great Bend Prairie, South Central Kansas, and the Ogallala portion of the high plains. More recharge, shallower to the water. The Ogallala, we generally see a deficit environment every year, but not everywhere. Other areas are a little higher than other places. And those declines got accentuated by drought conditions. The drought influences the drought influences pumping patterns, and that pumping patterns influences then what changes in the water table. Generally, we see our highest groundwater declines south of the Ark River. You also see them running up through Liberal, through Hugoton, up into Johnson City, Wallace County a little bit, west of Goodland, between Hoxie and Colby. We see some significant groundwater declines. And that lines up with this map, which is showing where that water is pumped on the highest densities on average in terms of groundwater diversions. And they relate to one another very well. Where we have higher levels of use, we have generally higher levels of decline. But we're just talking about groundwater declines here. With a groundwater system, you need to start talking about water and storage. And so the way we do that, we use a quick way to look at that, we call what the saturated thickness is. You already saw the top of the aquifer with the water table. This other map on the other side represents the bottom, the shales that's holding that water up in place. You just subtract the two, and you get a map that we call the saturated thickness. And the saturated thickness is a proxy for us to use to get us an idea of how much water is in storage. So even though we may have had big groundwater declines, say in southwest Kansas, they may not be as significant as what you see up in other areas of the state because there's less water there in storage. So kind of marry these things two together to bring them together. We try to look at water level change with what we call in storage. And we came up with a concept called the estimated usable lifetime. And basically what the estimated usable lifetime does is it tries to take a groundwater change that we saw over some period of time, and then we say, okay, here's our current level of storage we have in a certain place. We know it's not going to last forever, but we also know that we're not going to pump this all the way down to the zero. We don't go to zeros. At some point it levels off. We have a threshold there. And so one of the thresholds we come up with is to say, let's say at 30 feet of saturated thickness. At that point, our well yield starts to change, and we can't pump the water like we used to. So if we had a 20-foot drop in 10 years, we can say it dropped 2 feet annually. We project that out in the future, and what that gives us then is a 10-year usable lifetime. We're not going down to zero. We're just kind of at some point that's going to level off and flatten out. And so what we're doing here is we're just projecting forward a groundwater change. We're not doing climate modeling or anything like that. Just taking a change, shooting it forward to a set amount of water in storage and seeing how long it is till we get to a certain threshold. And so I'll give you a little hint on public speaking. When they say you have 10 minutes, you don't show maps like this that take 15 minutes to describe because there's a lot of stuff that goes on here. But what this is trying to do is show you if we saw water level changes that we saw during the 2000s, if we shoot those forward today, how long will it be until well yields start to flatten off and we can't get 400 gallons per minute? Why 400 gallons per minute? That's kind of the lower end you need for a center pivot system. So we're not measuring the zero value here, we're measuring the usable for the large volume uses, and that's primarily being irrigation. Again, this methodology doesn't really fit South Central Kansas. It's a little bit different system. You can apply it to the Ogallala. So the red areas and the orange areas are about 25 to 50 years if we saw the same water level declines we saw in the past get repeated. Some of the areas are brown. They're already at that threshold. In the case of northwest Kansas and some other areas, it was that way back in the 40s. But maybe some of the areas of west central Kansas, say Scott City area, you know, it's not the same as it was. You're not getting thousands of gallons all summer long. It's going down, measured in hundreds, if not hundreds of gallons per minute. So we're trying to measure not zero, but where do our well yields suffer? There's still water there, but where does it become impractical to pump at very large volumes? So with that, I will turn it over to Bill Golden. Thank you.